Good afternoon, class. This is a video discussing the transfer of heat into and out of a system and its surroundings. We refer to this as internal energy. So here's a quick picture. If I have a system here, energy leaves the system into the surroundings. Surroundings are around it. It includes everything. I have energy leaving it. This is going out of the system. We call that a negative sign. We always have the system as its reference. If we have energy going into the system, we refer to that as the positive sign. Not saying that this denotes the difference between a positive number and a negative number, just that it's more of directional than anything. We're moving energy out, it's negative. We're adding energy in, it's positive. Cool. So, refer to this table. Learn that. It's really important. Let's highlight it. This is important. Learn that. And let's go from there. So here's a quick example. I'm not going to go over. You can go over that on your own. I do want to talk about this practice exercise too. So, to calculate the change of internal energy for a process in which system absorbs 140 joules and does 85 joules of work on the surroundings. Okay, so what do we have? Practice example 2. So we have internal energy of a system. We added 140 joules of heat energy into the system and lost 85 joules of work out of the system. Excellent. So initially we look at this and we're saying, okay, now we have, if we draw a picture of our system, we have some energy coming in, 140 joules, some energy coming out, 85 joules. Now, because it's coming out of the system, we're going to give that a negative sign, directional. This is going in, it's going to be positive. So I know in the question it says that it's positive 85 joules. Well, that's just a number. Now we're going to use our equation with a direction. So our equation, the change of energy of an internal system is equal to Q plus W, which is equal to 140 joules plus a negative 85 joules of work that's going out of the system. Add those two together, or subtract those two. What do we get? About 55 joules of total energy is added. So this is telling us that overall the net gain of energy is positive. If the net gain of energy is positive, that means the overall process itself, well, that's endergonic. Double check that, well, we have a positive 55. So energy has been added to the system, it's endergonic. The other vocab word that we talked about this week is exergonic. Yep. And this is not that. This is endergonic. So, cool. Excellent. Great question. Something like this might show up on a quiz sooner than later, like Thursday. So let's see here. Scrolling down, practice exercise 5.3. Excellent description of questions that I like to give on quizzes. And I'm going to go over specifically, again, practice exercise 2. Calculate the work in joules. The volume of system contracts from 155 to 0.85 at a constant pressure of 0.985 ATMs. Now, when we're talking about work, we're talking about changing energy without necessarily changing the internal heat, or changing the heat, or changing the temperature directly. So another form of work for our case as chemists is pressure and volume. And we talked about this in the gas laws. Work is the change in pressure and volume, and specifically at a constant pressure is the change in volume. Okay, so scroll up here real quick. So this is 2b, I guess. We have work equal to negative P delta V. And this is work on a system of a contracting system. So a contracting system, well, I have a balloon at this size, 1.55 liters, and it's going to contract for some reason to 0.85 liters. And this poor balloon got crushed, right? All this energy from the surroundings was greater than what it can withhold, and shrinks the balloon. So let's just plug and chug. The work is equal to negative 0.985 times delta V. Now what's delta V? Delta is change, okay, and change, as we remembered, is final minus initial. And for our case, our final volume, 0.85 minus our initial volume, 1.55. This tells me that negative 0.75 was my change in volume. I mean, my volume went down 0.75. Now this is different than the last example. This isn't telling us that energy has been transferred yet. We're just still trying to tell us the direction of the volume changing. So this doesn't refer to volume leaving the system. All right, this is if the volume has changed. All right, cool. So where are we? W is equal to negative 0.985 times negative 0.75. Cool. And that leaves us with work equaling 0.685. And my units in this case, liters times ATM. Now, where did I get that? Well, if, let's see here. Here, ATM is the pressure and volume is liters, leaving me with liters ATM or ATM liters. So same difference. So, but that's not what we're asked for. We're asked for the answer in joules. So we have to convert this to joules. And to do that, we have a conversion factor. This might look familiar to you. We have 1 ATM is equal to 101.3 joules of energy. All right, let's convert. We'll have 0.685 LATM, 1 liter ATM is equal to 101.3 joules. And that leaves us with, what is that? 69.8 joules of energy. Awesome. So, just a quick review. We calculated our change in energy, amount of work done, by isolating the change in pressure and volume. Now, we had a negative volume because it was contracting. That's cool. Multiply that by our negative P, we'll get a positive number. Our work was positive. Therefore, if the work is positive, that means energy went into the system, contracting it. So work is positive, went into the system, that makes sense. Also known as endergonic as well. All right. Let me know if you have any questions in class, and we will go over this again. Thanks. Have a great day.